So this video is for Integrated 3. This is covering the graphs from Friday that we were practicing on the graph paper I passed out. So what I would recommend is, as I read through these graph equations, write them down on your paper, pause the video, try to see if you can do these without my help, and then come back and restart the video and go through, and I'm going to show how to do each of these correctly and accurately. Okay, here we go. So the very first graph is y is equal to 2 to the power x minus 3 minus 4. This is an exponential function. The second one is also an exponential function. Y is equal to 12 times 1/2 to the power x plus 2 minus 6. So this first one here, our a is really a 1. Our b, or our multiplier, our base being raised to a power, is 2. So here we're timesing by 2 over and over again. And our a, since we don't have one that we see there, it's really a 1. This one here, our a, our initial value, is 12. And our multiplier, our b, our base, is 1/2. So we're timesing by 1/2 over and over again. Now down here we have an absolute value graph. Y is equal to 2/3 times the absolute value of x plus 4 plus 2. This one here is a circle. This is not a function. The rest of them we're graphing are functions. This one is not a function. It does not pass the vertical line test because x's have more than one output, or y, in this situation. So this circle is x minus 2 squared plus y minus 5 squared is equal to 16. Okay, on the back side, we have a reciprocal function. Y is equal to 1 over x plus 4 plus 3. We have a cubic function. Y is equal to the quantity x plus 5 cubed plus 2. We have a square root function. Y is equal to the square root of x minus 4 minus 3. So x minus 4 under the square root. And the last one here is a parabola. Y is equal to 1/2 times the quantity x minus 3 squared plus 2. So after you have those written down, pause the video and see if you can graph these, or at least find the locator points and think about what the shape of the graph is. And then once you attempt them, come back and restart the video. So right now, I am going to be going over the very first graph, this exponential. Now, for this exponential, we want to find a locator point. And that locator point I am going to identify from this quantity here, what makes this x minus 3, this exponent 0, which is a 3, comma, this -4. That's going to be my locator point. So I am going to plot that locator point. Okay, so I'm going to go to 3, -4. And that locator point is actually not going to be a point on my graph. In terms of the actual exponential, it's going to help me find where my start is, but also where my asymptote is. So for this, I am going to draw a horizontal line, which we call an asymptote, through that point. Okay, and that horizontal asymptote has the equation y is equal to -4. So that's the spot where the graph gets closer and closer to, but never crosses, never touches. Now, this locator point, let me just make it a little bit more noticeable here. This locator point, that's going to be where I'm going to start my graph. That's where I'm going to start my graph. So What I'm really doing at this point is this is kind of like where my 0, 0 would be. So what I mean by that is, since this graph is really 2 to a power, from that spot, I'm going to be starting going 2 to the 0. Then as I move over 1, 2 to the first. Then as I move over to 2 squared. And as I move over a third time, 2 to the fourth, and so on. So I'm really thinking of this as 0, 0. And so when I do 2 to the 0, I'm going to get a 1. Let me just get a bigger font here. And so I'm going to have that point right there. And as I go over 1 from my locator point, I'm thinking 2 to the first, and 2 to the first is 2. And as I go 2 from my asymptote, on my asymptote, but from my locator point, I'm going to do 2 to the second, which is 4. So I go 4 above. I'm going to go 1, 2, 3 from my locator point. That's going to be 2 cubed, which is 8. So 1, 2, 3, 4, 5, 6, 7, 8. Now my next one would be 2 to the fourth. When I go 4 away, that's going to be 16, which is going to be too high. Now what's really happening here is my initial value, 2 to the 0, or any base to the power of 0, is always going to be a 1. Okay, so I'm always starting 1 above when my A is a 1. And I just have my base to a power. And then since my multiplier is 2, I'm really timesing by 2. So if this first height is 1, as I go over, it's going to be, I take that height and double it, 2. I double that, 4. I double that, 8. When I say I double, I mean I multiply by 2. And I would double 8, which would put me 16 above, but that's going to be off my graph. Now, as I'm going backwards, since this is 8 and then 4, I'm really making it half as high. Okay, I'm dividing by a half. So if I wanted to plot another point on the other side, half of 1 is going to be a half, and then half of a half is a fourth, and so forth. Okay, but I want you guys to at least do it 2 to the 1 on to the right, and then we can just connect the rest. But as we connect it, it doesn't just stop at that one point. It continues, and it gets closer and closer, but doesn't cross our asymptote. And that's my exponential graph. So the next one is also an exponential graph. And this one has a stretch, or an A, our initial value of 12. Okay, so that's going to be different than the last graph. And our multiplier, or our B, our base, is 1/2. But I'm still going to find a locator point. And my locator point is going to be -2, comma, -6. -2, comma, -6. So that's where I'm going to go. So I'm going to go to -2, -6. I'm going to put my locator point. Okay, make it a little bit bigger so we can see it. That's my locator point. And then I am going to be drawing my horizontal asymptote through there. Okay, so my horizontal asymptote, as I'm dragging it through here, is going to have the equation y is equal to -6. And then from this locator point, that is where I am going to do the rest of, you're going to start my graph. So when my A is 12, from here, I am going to be starting 12 above my asymptote. Now, the reason why, if you think about the last problem, I started with 2 to the power 0. I'm really starting at 1/2 to the power 0. That's really what I'm thinking there, but that 12 in front is going to times that. So I'm doing 1/2 to the power 0, which is 1. So I get 12 times 1, which is going to give me 12. So every time I'm doing this, this base to the power 0 is going to be giving me a 1 times my stretch. So that's why this A This initial value is going to be the starting height above my asymptote. So I'm going to be starting 12 above. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's where I'm starting, 12 above my asymptote. And now I'm timesing by a half. I'm going to have half the height. So if my first height is 12, as I go to the right, because I'm timesing by whatever my base is as I go to the right. Okay. So as I go to the right one, half of 12 is going to be 6. So I'm 6 above. As I go over again, half of 6 is 3. So I go 3 above. Half of 3 is 1.5 and so forth. Okay. And then I'm going to connect this with my curve. You see that this is a decreasing exponential graph, decay, where the other one, because my base is between 0 and 1, where the other one up here, since my base is greater than 1, it is in growth, exponential growth. Okay. Here's this graph, just in case I didn't give you enough time to see it. Now I'm going to look at number 3. Number 3 is an absolute value graph. For the absolute value graph, okay, let me first find my locator point, and my locator point is going to be -4, 2. So I'm going to go to -4, 2. That's going to be my locator point. Now, in this case, that's actually going to be the vertex. I'll write vertex. I'm not going to write it in that font. The vertex of my absolute value. So I'm going to go to -4, 2. Now, this stretch is really a stretch, just like the other graphs, but when you're talking about linear situations like a line or this absolute value, which is a V, you can think about this stretch, this A, as a slope. So this is 2/3. So that means from here, I'm going to go up 2/3 in both directions. So up 2/3, up 2/3. Let me do the same over here, up 2/3. And then I can connect this. Let me not do it that fat. I can connect it. Okay, and again, it extends beyond. And that is our absolute value graph. Again, we only think of the stretch as a slope if it is absolute value. And the reason for that is a regular absolute value graph, if I graph it in red, a regular absolute value graph is going to be the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. The absolute value of 3 is 3. The absolute value of a -1 is 1. The absolute value of a -2 is 2. The absolute value of a -3 is 3, and so forth. So you see that what's happening is I'm going up 1 over 1, up 1 over 1, up 1 over 1 originally, okay, because my stretch is really a 1. So here, when I have this 2/3, now I'm going to go up 2/3, up 2/3. Okay, on number 4. Number 4 is a circle. So we still want to find the center. The center is actually not on our graph. Okay. The center is going to be what makes this 0, which is 2, and what makes this 0, which is 5. So I'm going to go to 2, 5. And then this is my radius squared. Okay, so this is r squared, okay, which is 16. So I need to take the square root. So my radius is going to be 4. So I am going to go to 2, 5. Okay, that is my center of my graph, or my locator point. And then I'm going to go out 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then I'm going to connect it with a circle. Now, since I am using Cami, you guys are doing it on paper, I can come here and get ellipse. And if I hold shift while I do it, I can start at the center of my circle and actually drag it out, and it will draw my circle for me. Okay. Let me try it again without letting go. Okay, there's my circle. And I'll just change it to the same color as the rest of my circle. Okay, there's my circle. Now on number 5, this one is a reciprocal function. And this one's going to have a locator point at whatever makes this denominator 0, because we can never have our denominator be 0. That will make it undefined. So that's going to be -4, and then the +3. Okay, so that's where my locator point is going to be. And when I plot that locator point, -4, 3, is actually going to be where my vertical and horizontal asymptotes are going to go. Okay, so I am going to have a horizontal asymptote here at 3. So that's going to be y = 3. And I'm going to have a vertical asymptote here at -4, x = -4. So let me write those equations down. So again, this one here, the horizontal one's always a y equal, and that's y = 3. My vertical one is going to be an x equal, so that's x = -4. And now I kind of think of this as kind of like my new xy axis, my new origin. And we spoke about it the other day, that really, if we're thinking about the basic parent graph or parent function of this reciprocal function, it would be y = 1 over x. But if I was to multiply that by x and that side by x, I would end up getting xy is equal to 1. So really, my two coordinates, my x and my y, multiply to 1. Okay. And so what is going to give me a 1? Well, one point would be having a 1 for my x and a 1 for my y. Another one would be having a -1 times a -1. So that would be my x and y. Now, I'm not starting at the origin. I am starting right here. Okay, right here at this locator point where these two asymptotes meet. So from here, I'm going to go over 1, up 1. That's the only point I'm going to need you to accurately plot. And again, from here, because this was a +1 times a +1 gets me a 1. A -1 times a -1 gets me a 1. So that's the other one. And then remember, these are the branches. I showed us how to do it with like a 12 to the power, a 12 over x the other day. And so then you're just going to draw it, getting closer and closer to these asymptotes, going through this point. And that's your reciprocal function. Now, on the next one, this one is a cubic graph. And this cubic graph has a locator point at -5, 2. So this is going to be at -5, 2. That's where my locator point is. So I am going to go to -5, 2. We call that an inflection point. Okay, we call that an inflection point. So -5, 2. Okay, and again, we call that, I'll write that here for you. We call that an inflection point, but it's our locator point. Inflection point. So now from here, I am going to be pretending that this is like my 0, 0. And I am going to be basically doing 1 cubed, 2 cubed, 3 cubed, -1 cubed, -2 cubed, -3 cubed. So I'm going to come back here. I'm going to go to 1 away. So I'm going 1 away. 1 cubed is 1. So I go 1 above. And I'm going to just change this color here for a second so that you can see the one that I am. That's my inflection point. It's a point on my graph, but I just want to make sure you see where it is. Okay. So that's where I'm always going. 1 away from 1 cubed is 1. 2 away from 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go -1. -1 cubed is -1. I'm going to go -2. -2 cubed is -8. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to connect this. And I'm going to connect it with a curve. Now that inflection point, what's happening when I draw this, I am, and let me make it a little thinner. I am thinking of it almost like half of a open down parabola until it gets to that inflection point. And then it's going to be changing concavity. It's going to be then almost like it's an open up half of a parabola. And that's my graph. And the last one no, actually we have this one and we have a parabola, sorry. So this one here is going to be a square root graph. And again, I want to find the locator point, and the locator point is going to be at 4 because that's what makes this 0, comma -3. Now remember, when we're doing a basic square root graph, I cannot square root a negative. So if I was in purple, just graphing y equal the square root of x, we need to remember that we can't square root a negative because we get an imaginary number. So the very first value we would be doing would have been a 0. And the square root of 0 is 0. And then from here, I'm just going to go out and 1, and I would do 2, but 2 is not a nice square root. So I go out 1, square root of 1 is 1. I go out 4, because that's nice. The square root of 4 is 2. I go out 9, and the square root of 9 is 3, and so forth. And then I would connect it. Well, I'm going to do the exact same thing, but starting at 4, comma, -3. So I'm going to go to 4, comma, -3. So this one in blue, this is going to be the one I'm graphing. And from here, I'm going to go out 1. And the square root of 1 is 1. So I'm going to go up 1. And then I go back to this point and I go out 4. 1, 2, 3, 4. And the square root of 4 is 2. So I go up 2. I would go out 9 from this, but I don't have room. And then the square root of 9 would be 3. So let me just connect it. And so this is going to look like half of a sideways parabola. But that is your square root. Notice that right here, this is not having an arrow because this is my start. I start at 4, -3, and then I go from there. On number 8, this one is a parabola. So for this one, I'm going to have 3, comma 2 as my locator point, but vertex. So I'm going to go to 3, comma 2. So 3, comma 2. I'm going to put that point there. This is like my 0, 0. This is where I'm going to start. I've already moved it right. I've moved it up. So now I'm just focusing on basically graphing y equal 1/2 x squared. So I'm going to just be going out 1, and I'm going to do 1 squared. And then I'm going to times it by 1/2. And I'm going to go out 2. I'm going to do 2 squared. and then times that by a half. So let's get started. So I go out 1 squared is 1, times that by a half, I'm going to go up a half. And I'm going to do the same on the other side, because when I square a -1, I also get a 1. So when I take half of 1, I'm also getting a half. Okay, I'm going to go out 2, 1, 2. 2 squared is 4, but half of 4 is 1, 2. I'm going to go out 1, 2, 3. 3 squared is 9, and half of 9 is 4.5. 1, 2, 3, 4, and a half. And the same on the other side. I'm going to go out 4, 1, 2, 3, 4. 4 squared is 16. Half of 16 is 8. 1, 2, 3, 4, 5, 6, 7, 8. And the same on the other side. And then remember, these are not V's, these are U's. So you want to draw it curved. You can see the curve when you see the points plotted accurately. And that's the graph. So hopefully this helps you guys out. I'm going to be making some individual videos on each different function that I also will be posting for you guys, probably in announcements, and maybe also have it in maybe notes down at our bottom notes module.